Good morning. Let's start our lecture under this module 4. Okay, can you see the presentation?
Yes, ma'am.
Okay. In the last class, we have seen what is minimum description length principle. Why we prefer this minimum description length? According to Occam's razor, if there are lots of hypotheses that are available for a particular learning problem, in that case, we have to prefer the best, we have to prefer the shortest solution as the best solution. Though we have multiple solutions, though we have multiple hypotheses, we should not prefer complex hypotheses, though they are making all the predictions exactly. We have to go for, we have to always opt for simpler solutions, though there are some errors associated with it. Why? Because it will increase the generalizability of the problem. It increases the generalizability of the learning model based on that particular hypothesis, right? So any statement that gives you 100% accurate predictions, rather than that, you always opt for a simple statement or simple hypothesis which gives you a good amount of accuracy, and you have to compromise with some errors, moderate number of errors. Okay. So Occam's razor suggests that always opt for a shorter, simpler hypothesis when compared to complex hypotheses which are not generalizable, though their prediction capability is high. Okay, this is called as minimum description length principle. In order to understand this, I have given you the example of telegram. When the telegram is being communicated, there they will try to find the shortest codes for frequently used words. Means most probable words will be given smaller codes so that the transmission will be cost effective. In the same way, here also we are trying to find out a hypothesis with minimum description length so that it will be easy for us to apply it in the larger scenario. Means for a larger population. Okay, not only for a sample, we can extensively start using that hypothesis because it is simple and easy to implement. Now in today's class, we are going to see naive-Bayes classifier based on naive-Bayes theorem. We have already covered about naive-Bayes theorem in the previous classes. You know what is naive-Bayes theorem, right? The posterior probability of the hypothesis given the training examples is nothing but the probability of D given H multiplied by the prior probability of H divided by the prior probability of D. Okay, now among all these posterior probabilities, whichever hypothesis has the highest probability, that is your maximum a posteriori hypothesis, which is indicated by H map. You remember this H map? How did you derive this H map? Among all the posterior probabilities calculated means you have some three hypotheses, three statements that you make in accordance with your training examples given. Means your learner, your machine learning model is given a set of training examples. Now based on the training examples, three hypotheses were made, three hypotheses were formulated or framed. We can say it as three statements are framed. Now among those three statements, which is best suitable to your training examples, which has the higher probability of being in consistency with the training examples, right? Probability of a hypothesis becoming true given the training examples is nothing but that statement becoming true means that statement being in consistency with the given training examples. Means that statement applying for all the training examples given. Right? Now, whichever hypothesis have maximum probability in such consistency, that will be your maximum a posteriori hypothesis, and that is indicated by H map. Right? And for that, we have formulated it as argmax of H belongs to H. Why we are using argmax? You want to maximize the probability of a hypothesis given the training examples. That is what you are interested in. That maximum probability hypothesis you are interested in. That is why you are using argmax, probability of D given H multiplied by probability of H. Denominator is omitted because you are just indicating there the probability of D but not probability of D in relation with H. That is why it stays constant until some hypothesis is specified. That is why the denominator is omitted, and finally you get H map as argmax of H belongs to the hypothesis space, probability of D given H multiplied by probability of H. Right? That is your maximum a posteriori hypothesis representation. Now let us see how they can be used to create a naive-Bayes classifier. Now, one highly practical Bayesian learning method is the naive-Bayes learner, what we have learned so far, often called the naive-Bayes classifier. That Bayes theorem, if it is used by a classifier to perform some classification, that we call it as naive-Bayes classifier. In some domains, its performance has been shown to be comparable to that of neural network and decision tree learning. Neural network and decision tree learning have their own pros and cons, right? Neural network, though it is hard to interpret, though it takes more training time, its evaluation time is very fast. It takes quicker decisions when compared to other learning models. For that, we select neural networks. But in decision tree learning, the training time is less, and even the interpretation of the model is very easy, but it tends to overfit, right? Like this, each of these learning models have their own advantages and disadvantages. Now, when compared to such learning models, in some of the domains, naive-Bayes classifiers performance is comparable with these other learning models like neural network and decision tree learning. Now, the naive-Bayes classifier applies to learning tasks where each instance X, means each training example X, is described by a conjunction of attribute values. Conjunction of attribute values means, say if you take the example of your friend liking water sport, there you have the sky is clear and the humidity is low and the outlook is the sky is overcast. Like that, you have some specific attributes, right? Now, all these attributes have to occur together. You have to consider them together. That is why we are saying conjunction. Now, if you take conjunction of attributes, sky is clear and humidity is low and rainy is and cloudy no, something like that. Okay, all attribute you take and you combine them using and means you have to check that whether all these attribute values are true. Disjunction means or any of the values are true, then it will give the outcome variable. But conjunction is more stricter implementation, right? So if you take conjunction of attribute values, the naive-Bayes classifier applies to learning tasks where each instance, each training example X is described by a conjunction of attribute values and where the target function f of x can take on any value from some finite set V. Say the finite set V has only two values, yes or no. In that case, we call it as a binary classification problem. In some cases, if this contains high, moderate, and low. Say there are three classes or multiple classes. In that case, we call it as multi-classification problem. If it has only two classes, then we call it as binary classification problem, right? Now, the target function f of x can take any value from some finite set v. This v contains the target labels, whether it is 2 or 3 or many, more than 3, right? This finite set v contains all the outcome variables, and the objective is to learn the target function f of x, which can take any of the values from this finite set v. Got it? Now, a set of training examples of the target function is provided, and a new instance is presented, described by the tuple of attribute values a1, a2, and so on up to an. Now, training examples are given. Even the target functions are provided, means the outcome labels are provided, whether yes or no, or whether high or moderate or low. The target function is also provided. Target labels are also provided. Now, a new instance is presented to the learner, described by the tuple of attribute values a1, a2, and so on up to an. Means, say the skies condition is given, the humidity status is given, the raining status is given, the outlook, whether that particular day temperature will change or not, that attribute value is given. Now, how prediction is done? The learner is now asked to predict the target value when this set of attribute values are given, or classification for this new instance. It may be, always it will not be a classification task, right? It may be sometimes a prediction task, like forecasting the weather, or estimating the sale price of a house, or estimating the stock price of a share, right? Like this, you may have classification or you may have regression problem. In that case, giving these attribute values of some new instance, till then the learner might not have seen that new instance, right? New data point is passed on to the learner now, and it has to predict about that, whether the outcome is yes or no, or whether the outcome is a specific value that has to be predicted, right? Now, the Bayesian approach, in this case, the Bayesian approach to classifying the new instance, what is given, is to assign the most probable target value, right? Whichever target value is associated with this combination of attributes, that is more likely to occur with this combination of attributes. So you assign that particular value. So the Bayesian approach here is to classify the new instance. The Bayesian approach of classifying the new instance is to assign the most probable target value, V map. We normally used to call it as H map, but because you're talking about a value in the target label set, we are just indicating this as V map. Okay, say if V consists of high, medium, and low. Now, if the for this combination of attributes, if H has highest probability of occurring with this combination, then you assign that to the target variable. Or to the new instance, if the set of attribute combinations will give rise to low, and this has highest probability of occurring with this combination of attributes rather than the other two attributes. In that case, this will be assigned as the target outcome, right? That is what is given here. V map is given as whichever target label has the highest probability of occurring with this training example given. With this, not training example, with this new instance, with the combination of attributes in this new instance given. Okay, so that will be assigned as the outcome label. Now, how that can be represented mathematically? V map, that is the value which has the highest probability, is represented as, you're maximizing again, you're maximizing the probability of the outcome variable, and that you're trying to assign to the new training new instance that is given. So this argmax from every instance of this value, target value set, means this value set. How you represent the probability? Probability of Vj, that particular outcome label occurring, given under what condition? The set of attributes that are given in the new instance. The set of attribute values that are given in the new instance. Did you understand clearly? What is the likelihood of this label appearing with the combination of these attributes? What is the likelihood? What is the probability of this label Bj given the set of attribute values? Which is having the maximum likelihood, which is having the maximum probability? That will be assigned as the target label. That is your V map. Okay. Now we can use Bayes' theorem to rewrite this expression as, how do you write this expression using Bayes' theorem? You remember Bayes' theorem, right? Posterior probability, probability of H given D is equal to probability of D given H multiplied by prior probability of H divided by prior probability of D. Right now it is very easy for you. If I wake you up in your sleep also, you should be able to tell very quickly what is Bayes' theorem. Now that Bayes' theorem you are using here in order to expand this. So how you are writing, how you are substituting Bayes' theorem here? Probability of, here Vj, say it is, you are using it for H, and all this set of attributes you are using it for D, for simplicity's sake, in order to understand how to substitute Bayes' theorem. Now what is Bayes' theorem? Probability of D given H. So this D, the set of all the attribute values you are giving, probability of D, that is probability of A1, A2 and so on up to AN, given the value, outcome variable, outcome label, that is Vj, given Vj multiplied by prior probability of Vj, irrespective of the attribute values given, how many of the outcome labels has S and how many of the outcome labels has no. You remember, say out of 14 training examples, if 9 of the examples have positive value S and 5 of the examples have negative values, no. In that case, probability of S is 9 by 14. Probability of no is 5 by 14, right? That is the prior probability of the outcome label, irrespective of the attribute values given, divided by probability of occurrence of those training attribute values, the new instance attribute values, irrespective of what is the outcome label. And that is a constant. That is why even in Bayes' theorem, when we are calculating the maximum a posteriori hypothesis, you remove the denominator. You remember, in same thing you can do here. This is not in relation with the outcome variable, so remove it. So you are left out only with the numerator, maximizing the probability of observing these training examples, these attribute values. You're maximizing the probability of these attribute values given the outcome label multiplied by the probability of the outcome label without considering any of the attribute values. Okay, that will give your V map. That is the probability of that particular outcome value occurring with the new instance that has to be classified. When we see an example, it will be more clear for you. Okay, now we could attempt to estimate the two terms in the above equation based on the training data. Right? We can calculate probability of Vj. We can calculate the product of probabilities. I'll explain you how we do that. Okay. Now it is easy to estimate each of probability of Vj. Now you can easily calculate probability of Vj, right? Probability of high, outcome variable high, probability of outcome label low, probability of outcome label moderate. Okay. All this can be easily calculated, because you have all the training examples given. From that you can count how many of the outcome labels are high, how many of the outcome labels are low, how many of the outcome labels are moderate. So you can easily calculate the prior probabilities, right? It is easy to estimate that, each of the probabilities of the outcome labels simply by counting the frequency with which each target value Vj occurs in the training data, as I said. Say S occurs for 9 times, no occurs for 5 times out of 14 training examples, then probability of S is 9 by 14 and probability of no is 5 by 14. Now, the naive-Bayes classifier is based on the simplifying assumption that the attribute values are conditionally independent given the target value. Given the target value, we are assuming that there is an assumption that is made under naive-Bayes classifier, that is, attribute values are conditionally independent given the target value. Means the target value that doesn't influence the attribute value combinations. It is conditionally independent. Attribute values are conditionally independent given the target value. Okay, that is the assumption we are making. Remember, always you have some assumptions associated with every learning model. You have seen that there are assumptions associated with decision tree algorithm. There are assumptions associated with neural networks. Here also in naive-Bayes classifier, you have an assumption that the attribute values here are conditionally independent of the target value. Okay, so there is no relationship between what combination of attribute values you find and what is its outcome label, so that you can predict it with high accuracy by making this assumption, right? So the probability of observing the conjunction means combination of A1, A2 and so on up to AN is just the product of the probabilities for the individual attributes, right? What is the product rule in probability? Probability of A and B occurring together, or probability of A given B, both probability of A and B occurring together is nothing but the product of probability of A given B multiplied by probability of B, or probability of B given A multiplied by probability of A. Refer to the product rule given to you in the first lecture of this module. Product rule of A and B is probability of A given B multiplied by probability of B divided by probability of A, or probability of B given A multiplied by probability of A. Divided by is not there. I just got confused with Bayes theorem. Extremely sorry. We can represent it as probability of A given B multiplied by probability of B, or probability of B given A multiplied by probability of A. That is the product rule, you remember? Now, the probability of observing the conjunction A1, A2 and so on up to AN is just the product of the probabilities for the individual attributes, right? So when you take probability of A1, A2 and so on up to AN, given the outcome label Vj is represented as the product of all the probabilities, individual probabilities of each of the attributes given Vj. Means probability of A1 given the outcome variable multiplied by probability of A2 given the outcome variable multiplied by probability of A3 given the outcome variable, and so on. That is how you represent. Say you have like this: probability of sunny, sky being sunny, comma, probability, humidity being high. Given the outcome label is S. How do you write this according to product rule? You write it as probability of sunny given S multiplied by probability of high given S. So this becomes probability of sunny given S multiplied by probability of high given S. This is how you write. This is generally represented with this formula. Probability of different attribute values given the outcome variable, given the outcome label, is nothing but product of each of those attribute values, product of probabilities of each of those attribute values given the outcome variable. That is why see here, probability of sunny comma high both being observed given the outcome value, outcome label is S, is probability of, individual probability of sunny given S multiplied by probability of high given S, right? That will be your representation for the product of probabilities. Now substituting this into equation 1, what is our equation 1? This one. This is our equation 1. V map equal to R max probability of observing all these attribute values given the outcome target value multiplied by probability of the target value. This into this equation we are substituting we have the approach used by the naive-Bayes classifier. Okay, so what is the naive-Bayes classifier? What does it mention? It says that probability of A1, A2 and so on up to AN given Vj is equal to product of probability of AI given Vj, right? That we are substituting here. So you got, in this case, you just, in this case, see, for this probability of A1, A2 and so on up to AN given Vj, for that we have this representation, right? So substitute in that this representation. That is why P of Vj, you just take it to the beginning. 1 second. See this P of Vj, you just drag it to the beginning so that this can be easily substituted without any confusion. So this P of Vj, when you have taken it to the beginning, now probability of A1, A2 and AN, A1, A2 and so on up to AN, A1, A2 and so on up to AN, given Vj, that is written as product of each of the attributes AI given Vj, right? This is substituted in the place of this one. Okay, so you get this naive-Bayes classifier as you're maximizing the probability of occurrence of an outcome label given the occurrence of the attribute values. Okay, that you are maximizing, and you have substituted this formula. This notation you have substituted here, where V and B denotes the target value output by the naive-Bayes classifier. What would be the target value which has the maximum probability of occurring in combination with these attribute values? That will be the outcome value, right? See, it is common sense also. If this combination of attributes are appearing for this outcome values more number of times, frequency is more, probability is more. In that case, for a new combination of attributes, if it is matching the existing attributes, okay, then their attribute outcome label also can be given here as the classification label, right? Means you are trying to prefer the highest probable outcome label for that combination of attributes. Okay, that is what is being indicated here. I'm just telling it in the form of a text. For this combination of attributes, this outcome label is mostly seen. That is why now for this new instance, as it is matching with this combination, even the outcome label also may match. Why? Because it is mostly appearing with this combination of attributes. That is expressed as you are trying to maximize the probability of occurrence of that target label given each of these probabilities are multiplied. Each of the probabilities of sunny, outcome label S, humidity high, outcome label S, outlook change, outcome label S. Each of these probabilities are multiplied, and it is further multiplied with probability of the outcome label, yes or no, and you're trying to maximize that, and that maximized outcome label will be your classification output. Got it? Now, to summarize, the naive-based learning method involves a learning step in which probability of the outcome label and probability of the attribute being observed with the outcome label together, these terms are estimated based on their frequencies over the training data. That is what I said. How many times they occur, that high is the probability. This combination is occurring very less, so its probability is very less. This combination, this attributes and this target value is occurring more number of times, so that probability is high. Got it? In that way, we are trying to calculate the probability of outcome value and the probability of observing an attribute with the outcome value. Okay. Now, the set of these estimates corresponds to the learned hypothesis. The set of these estimates, what we get, corresponds to the learned hypothesis, right? Now, once we have the hypothesis, you select the most probable hypothesis. Now, once you have the outcome labels, you select the most frequent outcome label. That is how we need to understand. This hypothesis is then used to classify each new instance by applying the rule in this equation. Right? Now, once you are given a new instance, you can find out probability of each of those attribute values with the outcome value and multiply all of them, and you further multiply it with the probability of the outcome variable, and wherever the probability is maximum, that will be the classification label. I'll show you in an example. You'll understand it better. Now, after understanding the example, after your class, just go back and understand the theory once again. Effort from your side is also very much required in courses having mathematical concepts. You can't simply absorb everything only by the lecture. You have to work from your side to understand every concept, first theoretically, then understand it with an illustration, and again go back to understand the theory more better and come back to the example to be well versed with the topic. Okay, this is like two iterations process. Understand the theory, go to the example, by example, understand the theory once again, and come back to the example. You will be very much clear about the concept, right? Now, whenever you want to calculate what is the highest probable outcome label, you have to calculate its existence with each of the attributes, multiply all of them, and further multiply it with the outcome labels probability, and whichever is having the highest probability, that will be the final classification that is made by the learning model, whether yes or no, whether high or moderate or low, like that. One interesting difference between naive-based learning method and other learning methods we have considered is that, what is the difference? There is no explicit search through the space of possible hypothesis. Did you observe? In finders, in candidate elimination, in neural networks, everywhere some search happens through the hypothesis space. But in naive-based classifier, you just calculate their probabilities, and whichever hypothesis is having the highest probability, that you're selecting automatically. You're not going and searching in the hypothesis space. Okay, that is the main difference. And instead, the hypothesis is formed without searching. How it is formed? Simply by counting the frequency of various data combinations within the training examples. Yes, for this combination, this outcome variable, this combination, this outcome variable. This happened 2 out of 10 times. So the probability is 0.2. Again, this combination occurs with this outcome variable 8 times. So this probability is 0.8. Then obviously, you will be able to make your predictions with some support, with some likelihood, because the probabilities are available. There is support for your statements that you make, right? Now let us take an illustrative example. This is the table that is given in your second chapter, finding out or classifying whether tennis will be played on a particular day given the weather conditions, outlook, temperature, humidity, and wind. Now let us apply the name-based classifier to a concept learning problem like this, classifying days according to whether someone will play tennis or not. So the learner will start learning from these 14 training examples, and whenever a new instance is given, it should be able to predict whether tennis will be played on that day or not with some good amount of accuracy. Here we use the name-based classifier and the training data from this table to classify the following novel instance. Novel instance means new instance. New instance is now provided because we trained the machine learning model already with the 14 training examples. Now we have given it a new instance. On a particular day, the outlook is sunny, temperature is cool, humidity is high, and wind is strong. Now on this day, whether tennis will be played or not. Let us see how this task is tackled by the name-based classifier. Now our task is to predict the target value yes or no for this particular training example. For this particular new instance. Right? Now to fit the current task, the target value V and B is given by, in order to estimate what is the outcome label for this new instance, the target value V and B can be calculated. V and B means the target value, whether it is yes or no. How this can be calculated? By using this formula. You know how this formula has been derived, right? By using the product rule, we have substituted probability of A1, A2 and so on up to AN given Vj. We represented it by using the product rule. Product of probability of each of these attributes appearing with the outcome variable. Now, into this formula, you just substitute all the values given in the new instance. Probability, did you observe here Vj, this Vj belongs to, means the outcome label set, the target label set belongs to yes or no, because it is a binary classification problem. Sometimes you may have multiple classes also. Here, because it is binary classification, you just have two outcomes, yes or no. Now, you have to calculate the probability of yes and the probability of no. Both the cases you have to calculate, right? V and B means what? You are calculating it for S, one outcome, and you are calculating it for the outcome no also, right? Now let us take the condition when we are calculating with S. Means what is the probability of this new instance's outcome label being S? What is the probability of this new instance's target label being S? That we are going to calculate first. Then calculate the probability of this instance's target label becoming no also. Now among these probabilities, whichever is highest, that you will assign. That target label you assign to this new instance. Okay. See, it is very easy to understand. Just consider this formula. Now we are calculating probability of yes and probability of no. Okay. So first probability of yes we are calculating for probability calculating multiplied by what are the attribute values given? Outlook sunny. So what is the first probability? Probability of outlook equal to sunny given the outcome label S. Probability of temperature cool given the outcome label S. Probability of humidity high given the outcome label S. Probability of wind equal to strong given the outcome label S. You are multiplying all of them. That is what we mean here, right? Each of the attribute values given the target label means observing each of these attribute values given the target label. What is its probability? that you are trying to find out. Okay, so how many probabilities totally you have to calculate? Probability of S 1, probability of outlook equal to Sunny given Vj 2, this is 3, this is 4, this is 5. 5 plus probability of no, again probability of outlook equal to sunny for no, probability of temperature equal to cool given no, again all these for no also you have to calculate, right? Means 1, 2, 3, 4, 5, another 5, total 10 probabilities you have to find out and substitute in this equation in order to get whether S has highest probability of becoming the target label or no has highest probability of becoming the target label for this new instance given. How do you calculate that? Notice in the final expression that AI has been instantiated using the particular attribute values of the new instance. We have written with respect to the new instance values. Now to calculate V and B, that is probability of S and probability of no, we now require how many probabilities to be calculated? 10 probabilities have to be calculated. 5 probabilities for S and 5 probabilities for no. Total 10 probabilities you have to calculate and substitute in the equation. Now, let us see a small example of substitution. Then it will be more clear for you. First, the probabilities of different target values can easily be estimated based on their frequencies over 14 training examples. So what is the probability of Vj when it is S and when it is no? That you are calculating first. So probability of when it is S is out of 14 training examples here, 1, 2, 3, 4, 5, 6, 7, 8, 9 has outcome label S and 5 of them has outcome label no. That is why probability of S is 9 out of 14. That is 0.64. Now probability of the outcome label no is 5 divided by 14. 5 out of 14 training examples has the target label as no. Right? So how do you calculate the probability? 5 by 14. It is 0.36. Similarly, we can estimate the conditional probabilities also. It is very easy to estimate because everything is given in the training data set, right? For example, let us take a small instance. Whenever the wind is equal to strong, means probability of wind equal to strong, given the outcome label is S. Means whenever the wind value is strong, along with it, if the outcome label is S, count them. Let us see. Here, wind value is strong, but outcome label is no. So let us not consider this. Wind value is strong, outcome label is S. Wind value is strong, outcome label is S. Count it. 1. Wind value is strong, outcome label is S. Count it. 2. Wind value is strong, outcome label is yes. Count it. 3. Now 3 out of total 14 training examples. 9 S examples, not 14. You're considering only S values, right? So 9 of the outcome value outcome labels are S, no? So you have to take probability of wind equal to strong given the outcome label is S. So there are 3 such combinations of strong and S out of total outcome labels being S, that is 9. So what is its probability? 0.33. Now, again calculate probability of wind strong when the outcome label is no. Total, how many of the outcome labels are no? 5. Out of them, how many of them have wind equal to strong? 3. This combination occurs for 3 times. Out of 5 total, no outcome labels. So the probability is 0.60. Now using this probability estimates and similar estimates for the remaining attribute values also. Now for the other attribute values also you can count. See, for outlook equal to sunny, given the outcome is yes. For outlook equal to sunny, given the outcome is no. You can calculate. In the same way for probability of temperature becoming cool, probability of temperature being cool, given outcome label is yes, given outcome label is no. Calculate both of the probabilities from the training example set. In the same way, you calculate all of the probabilities, all 10 probabilities. Now, V and B you are calculating when it is yes, and V and B you are calculating when it is no. That is nothing but you are calculating the probability of yes being the outcome label when for the given new instance, and the probability of the outcome label becoming no when the new instance is given. So how is it represented? Probability of S multiplied by product of each of these climatic conditions being observed when the outcome label is S. Substitute them. It is easy, right? You have already calculated when wind is strong and the outcome label is S. You know that it is 0.33. In the same way, this you may get as 0.57, something like that, and so on. Substitute all of them. Multiply all these terms. Finally, you will get the probability 0.0053. Again, calculate V and B when the outcome label is no. Means probability of not playing tennis, you write that is 5 by 14, and probability of the sky being sunny when tennis is not played. How many times did you observe that in the training example? The sky being sunny and the outcome label is no. How many times? That frequency you can take. You can calculate the probability of sunny given no, probability of cool given no, probability of high given no, probability of strong given no. You have already calculated here, 0.60. Now substituting them in this and multiplying all of them, you will get the probability as 0.0206. Now tell me, for the given instance, whether tennis will be played on that day or not, seeing the probabilities. Students, tennis will be played on that particular day or not? Which probability is higher? Which probability is higher in this both cases? Speak out. Which probability is higher? This one or this one? Should I teach you right from the decimal notation? Which probability is higher?
No.
No is higher. So for the given new instance, the outcome label will be predicted as no, right? Thus the naive-Bayes classifier assigns the target value play tennis equal to no to this new instance based on the probability estimates learned from the training data. This is an important calculation which may be given in your exams. So practice this. Take the training examples set, take a new instance and try to calculate the probability for that of the outcome variable for that new instance. Okay, you have to practice it a lot. Then you will, and other variants also may be given, not only same example, right? But if you practice with this example, I think the concept will be clear to you so that you can apply that knowledge to any type of other examples given. In the next class, we'll go through Bayesian belief networks and how it is different from naive-Bayes classifier. Now, can you quickly answer these questions? How to represent posterior probability of hypothesis? Posterior probability of hypothesis, how can you represent that? Probability of Students, probability of posterior probability of the hypothesis means probability of observing a hypothesis. Can you help me proceed? Probability of observing a hypothesis. Tell me. Given what? Given what? Given the training examples, D. Posterior probability of hypothesis can be represented as probability of H given D. Means probability of a statement becoming true for the given training examples given. For the given training examples. Okay. Now how to represent the prior probability of D? I have started from the basics of probability, students, and proceeded to the complex topics so that you will not feel the concept as new one. Prior probability of D, how can you represent this? Probability of what? Probability of D. Prior probability of D can be represented as P of D. All simple things, right? What we have been discussing from class 1 of this module. You're not able to answer that. What is the product rule of probability? Probability of A and B occurring together. What is the probability? Probability of A given B multiplied by probability of B, or you can also write it as probability of B given A multiplied by probability of A. This is called as the product rule. Any doubts in today's class? Students, shall we end the class then? Okay, we'll meet in the next class. Bye.